All right, everybody, welcome back. Hope you had a good break. Again, whole day of training yesterday and today, and so many great sessions. And it is such a pleasure and honor to host Thomas Grohser from US. And Thomas, thank you very much for joining us. Friends, Thomas has more than 26 years of experience with databases, specifically in SQL Server. He has been working almost across many industries: entertainment, pharmaceutical, and financial services. And his focus has been to make SQL Server more reliable, security wise, performance wise, and focus on scalability aspects. And today's topic, Thomas is presenting on the new feature in SQL Server 2019, which is hybrid pool. Thank you very much, Thomas, for taking out time out of your busy schedule and giving your knowledge and experience to the community. Over to you, Thomas.
Okay, thank you for selecting me to speak. Let me share my screen so we can start. You cannot share your screen.
Yes,
while
I have stopped. Now you can, yes.
Yeah, we're all new to that virtual thing. It's not definitely changes things. So I hope you can see my screen. It says hybrid buffer pool.
Absolutely.
And my name on it. Okay, are we ready to go? Or yeah, I think we are.
We're ready to go.
So hello, thank you for selecting me to speak at this conference. I hope everybody is well and safe. And today I'm going to talk about the new feature in 2019, the hybrid buffer pool. So before that, I have to click on my own screen. A little bit about me. I mean, I was already introduced, but if you run that query into the world, you will learn that Thomas Grohser is my name. I usually go by TG because that's easier to pronounce worldwide. I work for a company called Entity Data, which is basically a consulting company. And I'm with SQL Server forever. I started in 1994 on SQL 4.2 when 16-bit was end of the line. And I've pushed the limits of SQL Server ever since. I work a lot with Microsoft. Wrote a couple of chapters in some books, and I'm a 10-year Microsoft MVP on SQL Server Data Platform. So you can read all that once I've shared the slides. So let's not waste too much time on this. These are the knowledge partners that make this conference and this symposium possible. So let's take a few seconds to look at them and thank them for enabling free and great learning for everybody. So what we're going to talk about today, we need to make sure everybody listening is on the same page. So in the first part of the presentation, I will cover how SQL Server I works in a very, very high level view, but right at the light level so we understand why hybrid buffer pool can or cannot help us in some cases. Yeah. I will give a little bit of an overview of storage technology that you can see how we ended up with persistent memory and the hybrid buffer pool. I will quickly cover how the buffer pool features came into SQL Server since the beginning of time, and then dive deep into the hybrid buffer pool. Yeah, let's get started. And then, of course, you can ask me questions till someone kicks us off that channel. So, a second. What the hardest thing in my career was I needed to learn how to fairly compare stuff. Yeah, because when you listen to vendors, their product is always the best in the world and better than every other product. And in most cases, that's actually not a lie. It's true, but only from a very specific angle. And that might not be the angle you are looking at. So if you ask Intel right now, what's the fastest storage you can have? They tell you PMAP. If you ask me, yeah, but it depends. So so the hardest thing I have to learn is how to compare apples and oranges in the world. Yeah? And once I figured out how apples and oranges work, the vendors switched to things like this. How can we mix apples and oranges and make it harder for you to compare? And then some even invented apples that are oranges on the inside, and this is all thanks to Photoshop, so these fruits don't actually exist. And then the worst part is when these guys come in, they're called marketing, and they might disguise the apple and the orange and makes it really hard to compare. So this is the thing is, yeah. And if you're from the Boston area, which most of you are not, you know this guy. And yes, we noticed afterwards that he really looked like my slides, so I added that in. So the bad first. It's not the ugly part, it's the bad part. But I thought I start with the bad part because once you have the bad news, the good news is easier and more fun to take. The bad news is all the features in this talk, and I mean literally every feature, I'm not touching any feature that doesn't require Enterprise Edition. So a lot of people will not have that version of SQL Server to work with. And then, yeah, you're not going to have hybrid buffer pool or any of the other features I'm talking about, like buffer pool extensions and a few more. Yeah. So that's the sad news. Maybe Microsoft at someday changes their mind. Thing is, you can still do something with it, but it's not the ideal world. Good. So how does SQL Server perform I/O? Because that's the foundation, everything that I'm arguing about persistent memory is based on. So we need to learn that first. And the strange thing that most people don't know is that SQL Server is technically an in-memory database. So is Oracle or DB2. Yeah. What does this mean? That means they never manipulate the data on the disk. They always load it into memory, do the changes, and write it back. They never make the change directly on the storage. There are databases out there that do that, but not SQL Server or any of the other major relational databases. So what components do we have? We have a query processor that figures out what's the best way to run the query. He's basically the director of the whole show, and he figures out what to do. And we have our buffer pool, which is basically a chunk of memory inside our server that is used to cache the data that's on the data files. And on the data files, the data is organized in pages. And that's super simplified. In the real world, it's 100 times more complex, but that's as detailed as we're going to go on learning how I/O is. We have a couple of blocks here. So if we write a query that is select something from a database, what happens is it gets handed to the query processor, it compiles it, it figures out what's the best plan, and the query processor then asks the buffer pool, hey, I need this data for this query. Can you please give it to me? So they request it from the buffer pool. The buffer pool says, oops, I have no idea what that data is. I don't have it yet. So I'm going to read it from the data file. Data file gives the data back, and the page, a copy of the page in the exact same form as it's on disk, moves into the buffer pool. And just to be very clear, this is true for traditional row store. If we use in-memory OLTP or column store, that story changes a little. But for this talk, we are only looking at row store, yeah? Because otherwise it gets a little bit too complex. You can still use persistent memory with column store. It makes very little sense with in-memory OLTP. So data comes back in the buffer pool. Buffer pool gives it back to the query processor. Query processor does whatever it has to do with it and answers the question. And in reality, it's not one page. It's a lot of pages that get pulled into the buffer pool to satisfy an average query. Hundreds, thousands, sometimes a few. Yeah? So this is the process, and that repeats for each and every query. If the query runs again, and the data is already in the buffer pool, it doesn't have to pull it from the data file. So it will satisfy the query from the memory. So if you run the same stuff where the queries in the same range of data over and over again, over time, the chances are that data is already in memory. And that is very important to understand for the future, because if we read it 1,000,000 times, it only comes from disk once and not 1,000,000 times. So going back, let's do the same thing with an update statement. For an update statement, we need a couple of more components because we now need to be able to write and change the data. To do that, we need a transaction log file, which is also on disk. We need something called the log buffer, which is a very small couple of megabyte size of memory that is used to buffer the entries into the log file before they end up in the log file. We need a component called the log writer that actually transfers the data from the log buffer to the log file. Yeah, so we got a question here. I said if I said it's only Enterprise Edition, does it work on Developer Edition? Yes, it works. It works on Enterprise Edition, and Enterprise Edition and Developer Edition have the same features. So you can play around with it on your developer workstation, but to use it in production, you unfortunately need Enterprise Edition. So back to our update. So we run an update statement. Oops, when I answer the question, I have to click back. So we run an update statement, same as a select statement. It gets into the query processor, gets compiled. SQL Server finds a plan. Usually update statements are much easier, but same process. So comes up with a plan and it eats data. If the data is already in the buffer pool, it uses it there. If not, same as before, it has to move it in. Yeah. And it might need more than one data, so it needs the data. It returns the data to the query processor. So now the query processor makes the actual change and writes what it changes into the log buffer. At the same time, when it writes it to the log buffer, it modifies it in the buffer pool. So the P4 page in the buffer pool now became P4 prime, which is the same page as before, but it changed. The update statement might grow the data, and it might have to need to allocate another page, and all that stuff might all happen, but that's too complex for this case. Yeah, we keep it simple here to understand it. So the data is still in the log buffer, and so far our query hasn't finished because it hasn't hardened to the disk, because if right now we would lose power, that change would be lost. So what happens is, at some point, the log writer kicks in and looks in the log buffer. Is there anything to write? Yes. Our log entry number 1 needs to be written. So it pulls it out and writes it to the log file. And once it's in the log file, the log writer tells the log buffer, yep, I moved that. And the query processor is waiting for that little bit flip in the log buffer that says, yep, that one is now written to disk. And I can commit the query. So you see that in an update, there's very little going on the actual data, but a lot is going on writing that change to the transaction log. Right? So practically, the speed of changes in the database just depends how fast you can write to the log file. So we got another question. The question is, how is the data written to the log file? In pages or something else? It's something else. So the definition that the actual bits in the log file are not publicly documented, but what people figured out through reverse engineering and through documentation over the years. How the data is written to the log file. It's written in multiples of the logical and physical sector size of the disk, which is either 512 or 4 kilobytes, 512 bytes or 4 kilobytes. And the log buffer writes, the log writer writes as much as it can in one go, up to 60 kilobytes. And yes, 60, not 64. Nobody knows why. Nobody will ever change it. So somewhere between 512 bytes and 64 and 60 kilobytes are written in one go. In the very early versions of SQL Server, and we're talking 4 point something, the log file was actually inside a regular data file and was just another table. But that changed because that turned out to be not very, very good. Yeah, but these days, every version of SQL Server is still in running. I hope that you're not having version 4 point something around. Writes it in some things. So more questions. The next one is, how often does the log writer query write queries to the log buffer? As fast as it can. It always does one at a time. Yeah, so it grabs as much data as is there. If 10 transactions wrote data in, and these 10 transactions have less than 60 kilobytes of data, it will grab all 10 and write them all down. Yeah, it does it often. Yeah, and it really depends on your system, and we'll talk about this later, how we can actually speed that up with minutes. And the next question I will not answer because I will answer it on one of the next slides. So we'll skip that and then I'll just click it over. So, and someone at a later point in time that for P4 prime, that page will be written back to the data file if it's dirty. So to answer the next question, and the thing is, what if the buffer pool is full already and the data doesn't fit in? So we have a full buffer pool, lots of pages in there, in memory, they're in a complete random order, there's not specific thing is, but there's matching pages on the disks. So if the selection comes in, query processor does its work as before, ask the buffer pool to pull in page 7, I think I did on my slides. So page 7 is not in the buffer pool, and SQL has a very efficient way of figuring that out. Then it says buffer pool, give me page 7. Buffer pool says, I don't have 7, but I don't have space for 7. So let me, sorry, 8. 7 is already here, page 8. So let me make some space. So it will write down page 4 because it was dirty before and make sure I have a clean copy in the database, and then ask the data file to retrieve the missing page, which is page 2, sorry. So this is how it works when the buffer pool is already full. It will have to make space. If it's lucky, it finds pages that were just read but not modified, then it just discards them and frees the memory. If not, it has to write it down and bring it back up. Again, a very time-consuming operation. And then the query is thing is. Same exact procedure with an update. Good. So I hope that answers the question that was asked here. And we're moving on. Query gets returned to the client. So how did storage evolve over time? Yeah, because to select the correct storage, and persistent memory is just a new form of storage, we have to kind of understand what type of storage is out there. It all started with a hard drive, and I didn't put in a picture of these really old hard drives from IBM that were like the size of a little house. I just put in things. So we're starting somewhere in the 90s, late 80s, early 90s, somewhere around that, where hard drives became a size that was kind of manageable and going in. Yeah, in the beginning, you had a computer, you had one hard drive, and everything you had was stored on there. Yeah? Over time, people realized, yeah, that's not very secure, because if that hard drive fails, all my data is gone. So people started to put multiple hard drives in for 2 reasons. A, security of the data, so you can now have a parity, a copy of the data, whatever you need. And you also gain some speed because, yes, 3 hard drives are faster than 1 hard drive. That's very simple to understand concept. Yeah. After a while, they figured out filling up these servers is really hard because servers have a limited amount of space. So can we do something else? And they invented the storage array, which is not to be confused with a network attached storage. The very first storage arrays had hundreds of hard drives in them. And then at the back side of the storage array, they had regular SCSI cables that went back to the servers, and the server still had the same controller as before. It just saw a virtual hard drive from that array instead of individual hard drives inside the server. But technically, it was the same technology. There was no network yet involved. Yeah? So this is how that happened. And then, of course, someone invented fiber channel and SANs were born, where basically you put the data on a SAN, and then you have regular network cables that can be very long, but as the storage arrays, they still had like the 6-7 meter limit, how far they could be away from a server. A SAN can literally be on the other side of the data center and it will still work. So they came up with the idea, let's put the data there. And at that time, the network was so much faster than the individual hard drive that it didn't matter, yeah, putting the network in between. Yeah, it still helped a lot of people. But then time went by, networks got faster and hard drives got faster, and kind of SANs hit it off because the industry put a lot of marketing into selling them. But especially database people noticed one thing with the SAN: the latency when writing to the disk was really bad normally. On a direct attached drive, you had 1 or 2 milliseconds to write to the controller cache, and you had 5-6 milliseconds to the disk. And on the SAN, sometimes it was 10, 15, 20, 25 milliseconds. If the SANs were really busy, this could go up to a couple of 100 milliseconds. And that started hurting databases. So, clever company figured out, hey, memory is faster than SAN disks. Can we build a SAN array that is completely made out of memory? And there's one company from Texas Memory. They came up with this crazy idea. To make a device that is completely made out of memory and is still the SAN, yeah? Which was a crazy idea at the time because we are talking before the year 2000. Yeah? So this was insane. It cost millions of dollars. And since they decided to not put it inside the server, but to put it on a SAN, the latency of the network really become a costly addition to that. Yeah? So they tried to optimize that. They directly connected it to the servers. But since they're no longer around, it wasn't a really viable product for the masses that would make any sense. Then a little company developed a device called Fusion.io, which was basically, they figured out, hey, we can do what Ramsen is doing. We're putting some chips that are something like memory, but the chips keep the memory. We call them flash storage. We put that on an extension card and put it inside the server. And the first ones came out like in gigabyte sizes, yeah? Where at the same time you could already buy a terabyte hard drive. But they came out with like 80 gigabyte drives. But man, were these drives fast, yeah? You could do hundreds of thousands of IOPS on one of these Fusion.io cards, whereas a regular hard drive can probably do 200. Yeah. So this was, I think is. So Fusion.io thing is. Okay, great. So then some clever people figured out, hey, we can take what Fusion.io does and put it in the case of a normal hard drive. This is when the SSD, the storage solid state disk, was born. Yeah? So they took the chips that were on the Fusion.io card and put it in a regular hard drive, gave it the interface of a regular hard drive. Great, worked fine, was much faster, had a lot of, the first generations had a lot of disadvantages with wear level times, and it died quickly. And people very quickly figured out this stuff is limited by the way the interface is actually the limit, because that SATA or SCSI interface that were on the early drives, which was designed to handle a couple of megabytes per second write and read speed from the drive, from the hard drives, but on SSDs, it was just not fast enough. So, and then at the end of my legacy, and I know some people will kill me that work for that company, but I already consider it legacy in my world. They came out and says, hey, we can combine SAN and SSDs and make it an all-flash array. So they basically took the RAM SAN idea, but instead of using memory that was insanely expensive, they used solid-state storage at the time. And they added lots of features, which are great. And if you need any of these features, you still will use that. But if it comes to raw performance, that's not their target. They want to give you features, same as SAN, snapshots and all kinds of things. Yeah. So that's the legacy of how storage developed over time. In modern systems that I design, none of these will be used anymore. All this is, I would not put it in as, if I have an old system, I might use one of these to make it a little bit better. But in a new system, I will not consider any of these items anymore. Yeah? And here is why. If you go back into the 80s, a hard drive had 40 megabytes in size. It could read 600 kilobytes per second, had a 27 millisecond latency for a single read, and the interface could do 5 megabytes per second. Great. Yeah. So in today's world, to save this presentation, it would take like an hour. Yeah. The video from that presentation. So there's no point. Yeah. On the other end of the spectrum, you take that all-flash array, which can store way over a petabyte, has 8 gigabytes per second transfer speed compared to 600 kilobits per second, has 0.2 milliseconds of latency, and the interface that your computer can talk to it has 2 gigabytes per second. So we already have a disparity here that the system can actually process data faster than they give it to you an interface. You can use multiple of these. So why is this bad? It looks good. It looks so much bigger, faster, everything. No, it's not fast. It's actually slower. Back in the days, it took 10 minutes to fill that 40 megabyte drive with data. Yeah. So this was the capacity of the system, and it took 10 minutes to use the capacity. That all-flash array, if you connect through a single interface, it will take you a day and a half to read the whole data. In my eyes, that's much fun. Yes, it's more data, but that's the time. So what happened with storage is that over time, storage capacity grew exponential. I mean, this is thousands and millions of times more storage than before, but only a few times more on performance. Yeah, that's only 500 times more performance. Sorry, 400 times more performance. So what to do about it? What's the current storage options that we have? NVMe disks, which is basically the involvement of an SSD. The bottleneck in an SSD was that they used the legacy SATA, SAS, or SCSI interface to talk to the drive, and these interfaces were not built. These interfaces are now slowly catching up, but then getting nowhere near where an NVMe drive is. An NVMe drive basically connects directly to the CPU as the Fusion IO card did, just for a much, much, much lower price. Yeah. So it's basically some chips on something and an interface inside your server where it can connect directly to the PCI bus, which might just be the PCI bus for some drives, or it is newer interfaces where it's just the connector is different. The electrical interface is the same, M.2 PCI Express slots, or there are some cable versions of it where you can put the drives in. NVMe can also be a PCI Express card, which is basically looks like this. It's a card that goes directly into your PCI slots in your workstation or your server. Yes. So the next one is called an NVDIMM. This is one of my favorites. It's literally a memory chip where someone had the idea, what if we attach a big ass battery to that chip? And this is an actual photo from one of the servers I had. The battery is actually much larger than the memory chip. So what happens is, even if the computer loses power, that memory chip keeps storing the data. You can even plug it out, pull it out, move to another server, put it back in there, and then read the data out if the rest of your server will not. This idea was genius. Yeah. So this was the first thing is, we can have storage at the speed of memory but it doesn't lose its data. And then Intel had the idea, yeah, that's great. Let's build storage RAM chips that have that and that don't need a battery. And that is what persistent memory is. The official name is Obtained Data Center Persistent Memory. Most people in the industry just call it PMEM for persistent memory because that other word you don't want to write or say all the time. Yeah? So here we're going to talk going on from now, NVMe, NVDIMM, and persistent memory. The first one, the closest thing we have to a hard drive. The second one, the closest thing we have to a memory chip. And the third one, the brand new stuff that is somewhere in between the two. So where are they? Performance-wise, NV and PCI cards are limited only by the PCI Express bus. Yeah. And they can be, for now, the largest one you can buy are 16 terabytes. The majority of them is between 2 and 4 terabytes. 8 terabytes are coming more and more. And the thing is, yeah. NVMe disks that don't use PCI Express bus directly, that are connected with cables or M2 interfaces, are limited up to 7 gigabytes per second. If they're on the PCI Express bus right now, they're on 14 gigabytes per second. The next generation that will double that to 28 to 30 gigabytes per second is on its way. But right now, the CPUs literally can't keep up with that speed. So Intel and AMD have to put a little bit more work in that to make that happen. But it will eventually happen. So persistent memory, how much can you have? And that's a nasty formula. You can have between 1 and 8 CPUs. Each CPU can have between 1 and 12 persistent memory chips. And each of these chips can have 128 to 512 gigabytes. So theoretically, you can put 48 terabytes of persistent memory in a single box. First of all, whoever signs your checks will put you away for insanity if you ask for that, because that's insanely expensive. Yeah? Practically, in a 2 CPU machine, you can have around 5 to 7 terabytes, which is still a lot, yeah? And practically. NVDIMMs, the ones with memory, the same tricky, 1 to 8 CPUs, 1 to 12 chips per CPU, and then that's why they never became popular. They came between 8 and 16 gigabytes in size, so you're technically limited to 1.5 terabytes. It's the fastest solution on the planet right now, but 1.5 terabytes is not a lot. Yeah? Databases today can easily be bigger. So back to our, how long does it take to save 16 terabytes? Hey, on an NVMe drive, about 40 minutes. We're back to where we were 50 years ago. We can save a whole hard drive in about 40 minutes, which is not bad if you have that. And the nice thing is, if you put 2 in a server, 32 terabytes, 80 minutes, still 40 minutes, because they work in parallel and it doesn't go up. Yeah. So anyways. PCI Express bus, since it's twice as fast, it's about 20 minutes. And this is getting awesome. Persistent memory, the 48 terabytes, we can save in 300 seconds, also known as 5 minutes. Yeah, this is getting really nice. And then the 1.5 terabytes in NVDIMM, we could technically save somewhere in 3 seconds if we had something where we can put it. But that means also, if we have the NVDIMM, it's not about writing, it's also about reading. Yeah? So this is the time when you have these systems and you fill them full with data, how long it will take to actually read all the data. 48 terabytes in 5 minutes is not bad. Yeah? Combine that with some clever query tuning and you will have some awesome results. So if you stack a petabyte of NVMe drives into a server, which you can do, you can read it in 2.5 hours. That's much better than 1.5 days. Yeah, that we had on the external storage system. And this is why I classified these storage systems as legacy in my book. Yeah? They're still wide out there and lots of people use them, but I design high-end systems, so I stopped using them. And the latency on all of that stuff is measured in microseconds and nanoseconds. Milliseconds are gone. I always laugh if people complain I have so many milliseconds. Just the fact that you're still measuring storage in milliseconds shows me that you are using the wrong tool for your job. Yeah. This is NVMe drives are dirt cheap. Yeah. I have servers that have 120 terabytes of databases on it, and these servers cost less than $70,000, including the storage that is built in, and that storage at the performance of NVMe drives. Yeah. So if you compare that to the millions of dollars that these external SANs costing, and they're giving you lower speed, this is why I consider them not current anymore. So moving on. With persistent memory, you have two options how to use it. Yeah? So you have the 12 chips in your system, and half of them can be persistent memory. The other half has to be things. There's some new boards that allow you to have more persistent memory chips, but I would not go for more than half. So that means you have 6 times 512, which is 7 terabytes, and you have 6 times 128 gigabytes, which is a little bit less than a terabyte. Yeah. So that's what's in your system. So in mode 1, which is memory mode, your operating system will see 6 terabytes of memory, which sounds great. What the CPU sees is 6 terabytes of memory with 768 gigabytes of level 4 cache. So what they're using is they're using the regular memory as cache for the persistent memory. If you turn off the power, all data is gone. The chips will be wiped when you turn it back on. This is just to put cheaper memory into your system and have applications that have no clue what persistent memory is, just use it. Yeah. So what this would basically do is it would increase your buffer pool from a possible 1.5 terabytes, because you could have the 6, instead of 6 times 128 gigabytes, you could have 12, which is 1.5 terabytes on a single CPU, which would replace that with the 6 terabytes that you have, which might be good or not. We will see, because we haven't talked about the performance of persistent memory yet. The second one is called application direct mode, and this is what SQL Server does. SQL Server, when configured to do so and finds persistent memory, the operating system sees the 6 terabytes of what they call DAX storage, and DAX is for direct access memory. Yeah, direct access storage. Yeah, and yes, and the OS sees 768 gigabytes of memory. So SQL Server would say, hey, there's another hard drive of 6 terabytes. Yep, I might use it if someone configures me to do so. And there is 3/4 of a terabyte of memory for the buffer pool. Never use memory mode for SQL Server. It makes SQL Server insanely slow, because if you use that, SQL Server would randomly put stuff anywhere, and because SQL assumes that all memory is the same speed, and to emphasize that, do not use, or he will not talk to you. Yeah, this is the guy at Microsoft that actually implemented these features, so he will be not talking. He did not look happy when I asked him that question. So moving on, buffer pool features over time. This is very quick. We start in SQL 4.21. We could have a buffer pool of 2 gigabytes. Nobody on the planet at that time had 2 gigabytes of memory. My first SQL Server had 4 megabytes of memory at the time. Yeah? And then we upgraded it to 8 megabytes. And this was running like legitimate databases. Yeah? Can you imagine this today? Today there's queries that are larger than 8 megabytes in just a query text. Yeah? SQL 7 moved the buffer pool to use 8 kilobyte pages instead of 2 kilobyte pages. Was a major difference, and that's actually the first version that actually was written by Microsoft. SQL 4 was still Sybase, and Microsoft just licensed it. And you could go up to 64 gigabytes when you had the right server, which again at this time was you needed to be a gazillionaire to afford that. SQL 2000 introduced non-uniform memory architecture, so CPUs could independently talk to the memory, and it introduced a 64-bit version on Itanium, which allowed you to have 2 terabytes of memory. And at that time, I actually worked for a company. We had 256 gigabytes at the time, yeah, because we asked the vendor how much it would be for 2 terabytes, and that was more than the company had revenue in a year. So that's not going to happen. Yeah? 5 years later, and they introduced something called the merry-go-round piggyback scan into the buffer pool, which I have a whole presentation on. Just shameless plug for other times. In 2005, 5 years later, x64 came out and made 2 terabytes possible on a regular CPU. And at that time, I actually had an Itanium system with 2 terabytes. It cost more than $10 million at the time. Thing is, by the way, 2 terabytes today is around $10,000. Yeah, so things changed a little bit. Yeah. 2008 allowed us to use large page allocations, meaning we didn't have to talk to the operating system in 64 kilobytes anymore to get 2 terabytes, which took about 45 minutes. You could ask the OS, hey, give me 4 terabytes at a time. Much more fun. And yes, in SQL 2014, they introduced something called buffer pool extensions. In 2012, there were no major changes. In 2016, they added NVDIM support for the tail of the log, which we will cover soon. And in 2019, the hybrid buffer pool. So let's have a look at the last 3 features. Buffer pool extensions. We had our hard drives, we had our memory, and now there were SSDs at the time. Yeah. So what can you do? The idea is you have your data file with your pages on it. You have your buffer pool, which we now call the level 1 cache for data. And then you could create a buffer pool extension, which was basically a file on an SSD. And what happened is, if the query processor asked for a page from the data file, it came into memory. And if this page was accessed a lot, but not enough to keep it in memory, like it needed, the buffer pool was full and it had to be moved back, instead of moving it back to the data file, they moved it to the buffer pool extension on the SSD. Yeah? And then if they needed it again, they pulled it back from the SSD. And then if it was removed from the buffer pool again, it came again from the SSD. If a page was not used at all for a long time, it actually was transferred back from the buffer pool extension to the data file eventually. So why are we not all using this feature? It sounds great. First of all, it's limited to 32 times the amount of memory the server has. So if you have a gigabyte of memory in your server, you can only add 32 gigabytes of buffer pool. And you could, if you have that's 16 times the physical RAM. So if you have 1 gigabyte of physical RAM, you can only have 16 gigabytes of buffer pool. And the other limit was you could only use 32 times as much memory as you had configured SQL Server to use. So if you used a dial to dial down SQL's maximum memory, because other applications were running on the server, so that reduced the size of the buffer pool again. So still, why is nobody using it? The timing when they released that feature in 2014 was terrible. When they started developing it, and everybody was really excited about it, SSDs still cost a fortune, and they were tiny. We're talking 60 gigabytes in sizes, 40 gigabytes, 20 gigabytes, hundreds of thousands of dollars. When they finished 2 years later, SSDs cost nothing because by then they were in every laptop. Yeah, and you could get hundreds of gigabytes of SSDs for almost no money. Yeah, and therefore, the size limitations of the buffer pool expansions made no sense. Also, memory dropped so much, yeah, that it was actually cheaper to buy the memory, use standard edition, than to buy enterprise edition and have the buffer pool extension. So very bad timing, great feature. I used it in a lab. We never moved it into production. I personally don't know any person that ever used it outside of a lab in real world. Maybe someone is around. Shoot me an email afterwards if you are. I love to hear your experience in production. It's just there. Nobody uses it. thing is. So next one, NVDIM tail of the log. We remember in the beginning, and now you will see why I had to go through these things at the beginning so we all understand how this works. So with an NVDIM and the tail of the log, we have our log file, we have our log buffer, and we have the log writer again. This is what we discussed before. But what if we put the log file on an NVDIM? How much faster could that write? The log writer could immediately write it because it literally has to move it from the left portion of the memory to the right portion of the memory, and your data is safe. And some people did that, and they had excellent results with it. But what if I tell you that SQL Server in 2016 had a feature, and it's still there, that you could put the actual log buffer on that chip, on that battery buffer chip. So that's called the tail of the log with an NVDIM. Yeah? Your server has to support it, the OS has to support it, but that's all the case. If you're on a current operating system on SQL 2016, you're good to go. So doing an update statement. As before, you ask the query processor asks the buffer pool, same thing as before. That's not what we're talking about. Query processor gets the data back, does the change, writes it into the log buffer, and from the log buffer gets back, yep, I got it, and it's safe because I have a battery that makes sure if we crash right now, nothing's lost, and the query processor can commit the update. This is so much faster. This is so insanely fast that you have no idea. Somewhere in the background, the log writer, as before, says, hey, there's something in the log buffer. Let me move that to the log file. Yeah? Nobody's waiting for me. I can do it whenever I feel like it. No pressure. I'll just do it so that this log buffer doesn't get too big and is too full. And just things. Yeah. Then, of course, you could go crazy and put the log file on another chip that has a battery as well. You shouldn't put them on the same, but you could do it theoretically. And of course I did because I'm crazy. So these are the results. So to compare that, I removed that one more time. So with the fastest SAN on the planet, flash array, everything, you can do about 3,500 log writes per second. And this answers the question before, how often is it done and how quickly is it done again? Yeah. With the fastest NVMe drive, you can do about 12,000 per second. Yeah. So these are the numbers. With a regular hard drive, you can do about 200 per second. Yeah. So this is a hard drive, 200 per second, fastest storage array on the planet, costs millions of dollars, about 3,500. A $2,000 NVMe drive can do 12,000, so a little bit faster and cheaper. Thing is, how much can an NVMe DIMM do? If I just put the chip and write it to the log file, the first one that we explored, instead of 12,000, I can do 187,000. Okay, so that's significantly faster. So we got 10 times faster. But if I actually use the NVDIMM for the log buffer, I can get to about 1.6 million. And this is just 1.6 million transactions on a single CPU on a single thing. Yeah? This is how fast it gets right now. So if everybody tells you SQL Server cannot handle a workload, they're just using the wrong hardware. And this chip is not expensive. This chip costs more than a regular memory chip, but it doesn't cost like massively more. Yeah. Let's say the normal memory chip in that size would be $100. This thing costs $500. Yeah. Compared to $1 million storage array that is way slower, I'll go for that. So, hybrid buffer pool. Finally, we arrive at the actual topic of the talk. Sorry for taking so long, but I think it was important so everybody is on the same page. So again, we have our query processor, we have our buffer pool, and the data file, and the data in it, and the buffer pool is in memory, and the data file, let's say, is already on an NVMe drive because we are modern people, but it could also be on a hard drive. And then we have this persistent memory. And this persistent memory can add the hybrid buffer pool. which is basically a data file that is treated as if it's in memory, because it is. It's on a memory chip. Yeah? So we have 6 pages down there. We have 2 more pages in our hybrid buffer pool. So what happens if we run a query? If we do select, same thing as before, query processor figures out how's the buffer pool, and the buffer pool says, yeah, I have that page. I'll give it back to you because we're reading page number 8. Yeah. So great. It just returns the result because it's in memory. If it needed one of the other pages, it will pull them back in as before. We don't have to go over that again. Works the same as before. But if it's in a file on the hybrid buffer pool, it immediately returns it, and the query is happy. No more moving from disk, no more moving around. Great. If it's a regular data, it pulls it in, and then in the future thing is. So the only thing they haven't figured out yet is how to change it in the hybrid buffer pool immediately. So if a query wants to update the page 8, for example, that's in the buffer pool, it will pull it into the buffer pool from the hybrid buffer pool, do the changes as before, and then, as with every other page, write it back to the disk file. Yeah. So on writes, you still have some moving, but you have moving from one memory to another memory. On reading, you get insane performance. So this is the difference on how NIO works when you have the hybrid buffer pool. So let's look at the requirements for hybrid buffer pool. First thing is you have to have a server that has persistent memory. Okay, makes sense. Second, you need Windows Server 2019. Any older version of Windows Server has no understanding of what persistent memory is, can't help you. You need SQL Server 2019. Yep, makes sense. First version that has that feature, so that's good. You need a volume on persistent memory that supports a file system that supports direct access memory, which NTFS is. There are certain file systems on Linux that support it too. It's a little bit tricky on Linux, but it works just as fine as on Windows. It's just not in the OS directly. You have to do something, but that's fine. And stranger thing, it has to be formatted with 2 megabyte cluster size. That's a new feature in Windows 2019 as well. Before that, the cluster size was limited to 64 kilobytes, which was always the recommended size for SQL. Now you have to do it in 2 megabytes. And that's the trickiest part that lots of people stumble across. The data file has to be a multiple of 2 megabytes in size on the volume. So you can't have a 3 megabyte file. You have to have a 2, 4, 6, 8, 10, whatever megabytes, gigabytes. Yeah. But if you have an odd number at the end in megabytes, it will not work. Yeah. And this has to do with how the file is aligned in memory and all that. So there's reasons for it, but too much detail for this talk. Yeah. So once you have all that, you're good to go. And by the way, you can create a new file or you can move an existing file. Doesn't matter. Yeah. So it doesn't have to be created there to work. For as far as SQL at this time is concerned, that's just another data file on some magic disk that is there. So how to actually get it running? First, you have to tell the instance, the server, that it's there. So auto server configuration set memory optimized hybrid buffer pool equals on. Great. Finally, Microsoft uses meaningful actual commands where the meaning is kind of thing. Yeah. And to turn it off, you can turn it off. Once you've turned it on for the server, it's still not used. Yeah. Microsoft wanted to make it really good. Then you can turn it on for a specific database. Yeah. So auto database set memory optimized is on. And yes, this sounds awfully like the same command is used for in-memory OLTP. And yes, it's confusingly close, but it's not. It's different command, but yes. We yelled at Microsoft for it, but nothing we can do about it. And then you can turn it off. So theoretically, you can turn it on and off for a database, the feature, and that is helpful when you want to figure out if it actually makes any sense. So, moving. There's in SUS configurations, you can figure out if it's if the first option for the instance is turned on or off. It will give you that line if it's there. And in SYS databases, they added another column, is memory optimized enabled. The moment it is, you can read that in SYS databases. So that's very helpful if you want to check if it's enabled or not. Yeah. So these are the 4, 5, 6 simple commands that they added in 2019 to actually enable that. Most of the feature is just once you turn it on, it works. Nothing you have to tune, change, or make anything. So how fast is this buffer pool actually? And I apologize, we need some algebra and calculus to figure that actually out. So I can't give you absolute numbers. I tried. Yeah. The problem is, to do that, I have to run extensive benchmarks. And unfortunately, the license agreement of SQL Server prohibits me from publishing a benchmark result. So I cannot tell you how fast in absolute numbers it is. I can tell you how fast it is relative to other stuff. Yeah. So what I found out over average 4 different vendors, that persistent memory is about 4 times slower than memory. So if something takes 1 second, if I do it in memory, it takes about 4 seconds to do it in persistent memory, and it takes about 16 seconds to do it from an NVMe disk. Yeah. So this is what we have roughly. Yeah. So NVMe disk, 4 times faster is persistent memory, 4 times faster is actual memory. So if we have, how much data do we have? And I already saw a question before, and I didn't answer it on purpose because we're getting here now, about what if my data, my table is actually bigger than the buffer pool. And this is the slide that will actually answer that. Yeah. So if your data is that you need to read in a query, yeah, is smaller than the buffer pool, and you run it the first time, the time the query will take is 16 times the time it takes in memory plus 1 time of the speed in memory. So 17 times of how long it would take if it is already in memory. Yeah. So it takes about 17 units of time. 16 to pull it from the disk, and 1 more time to process it in memory. So 17 units of time. Every access after that takes exactly 1 unit of time because it's already in the buffer pool. And since your data is less than the buffer pool in size, it will never disappear from the buffer pool until you turn off SQL Server. The thing is, so the average becomes this little formula in algebra. I will not bother you with it. And if you use calculus on it and calculate the limit, you will figure out that the longer you use it, the more the actual time goes to the actual time it takes to consult this in memory. Yes, the first time it's slower, but every time after that, it's just 1 unit of time. And if you run it a couple of million times, the first time doesn't matter. Yeah? So that's the result. If your data fits into memory, using persistent memory has no effect because you're better off having it on disk and then putting it into the buffer pool. Why? We get there. If it's in because if it's in persistent memory, it will take 4 units of time to process. Yeah. If it's in the buffer pool, if it's larger than the buffer pool, so you can't fit it in the buffer pool, that means every time you read it, it will take 17 units of time. Yeah. So okay, so if it's bigger than a buffer pool, it makes sense to put it in persistent memory because then it would only take 4 units of time. Great. But unfortunately, the hybrid buffer pool has a size limit. So it has to be larger than the maximum possible buffer pool, but smaller than the hybrid buffer pool can be. Then it's 4 units of time. Yeah. So if it fits, it's 1 unit. If it doesn't fit at all, it's 17 units of time. And if it fits in the hybrid buffer pool, it's 4 units. So this is basically the answer of a very long talk. And since I fully understand that that slide is massively confusing, I made a picture. So that picture will only contain these 3 things and these 3 things. So the conclusion. This is how much memory you have. This is the maximum amount of memory you can put in your server. That's one option. You make the buffer pool as big as possible. And then the second option is you cut your memory in half and instead put in more persistent memory. Yeah, that's what we talked before. You can have half the chips have to be memory. The other half of the chips has to be persistent memory, but they can be 4 times faster. And that's that big, long stretch. So if the workload does not fit into the larger amount of memory that you can have, but it fits in the PMEM, then it makes sense. So if we draw a diagram of the size of your data, if it fits in memory, it's red. Don't use persistent memory, yeah, because it fits in memory. It will be, that's the fastest you can go. There's nothing that, no other solution will make it go faster. Yeah. If it's in the size range of that persistent memory, it makes sense. Yeah. And if it's any larger, using persistent memory doesn't make sense anymore. So to emphasize that, the largest green portion is exactly as big as the persistent memory is. So that green range makes sense. Yeah? It doesn't fit in memory anymore, but it would still fit in persistent memory. And that's the small range. And this is a range of 1.5 to 6 terabytes. So if right now, till they have bigger chips. Yeah. So right now, if it's in that range of size and you have performance problems pulling it from the disk, putting in persistent memory will make your day. If your data is smaller, you will either see no difference or you will make it slower. If it's larger, you make it slower because you make the buffer pool smaller that you need to move the data in that doesn't fit in the persistent memory. There might be a sliver of place when you say, okay, most of my data fits in persistent memory and then others fits on regular disk, but this is splitting hairs. Yeah. And consider one thing, if you run out of hard drive space, you can buy another hard drive. If you run out of persistent memory space, you can buy as much more persistent memory as you want. There's no way of connecting it to your server. Yeah. So this is the whole thing. Questions now. So two or three, there's a bunch of questions. So the first one is an old one from the beginning, but I skipped it on purpose. So I said freeing up the buffer pool is a performance intense operation. Yes. Because if the buffer pool is actually full with pages that are all dirty, then it is a performance intense operation because it has to write it down. If the buffer pool is just full with read-only pages, yeah, it's quick. Get rid of it and use the next one. Yeah. So I misspoke a little bit there. I apologize. It's only a performance intense operation when the pages are modified and need to be written down. Yeah. So I did that. My table has doubled than the size of memory and scan happens in memory, how to store all the table pages into memory for query processing. If your table is twice as big as your memory, it's very simple. If it's less than persistent memory can help, you can put it in persistent memory, or you double your memory if that still works. Yeah, works. There's no magic. You can compress it. That might help you if your storage is really slow. But if you're already on NVMe, compressing will make it slower. Is it possible to implement buffer pool extensions without having SSD? Yes, but you might have a lot of performance issues then because SQL Server assumes that is on an SSD and it's not, and it's going to be horrible. You can put it on an NVMe drive or you could theoretically put it in a PMEM, but on a regular hard drive, I would not do that. That's the same question again, not answering again. What is the difference between NVMe DIMM, NBlock, and DAX? So I'm not 100% sure what the term NBlock means. So with NVMe, NVMe DIMM, not persistent memory. Sorry, with NDIMM, it makes sense to me. Sorry. So you remember me talking about, and I'm just going to go back in my slides because it's very simple. Lots of slides. Here we go. So DAX is used for the log file. NBlock is used for the log file at the bottom, and DAX is used for the log buffer in the middle of the screen. That's the big difference between nblock and DAX. So I hope that worked. What is the redundancy level for NVDIM? So NVDIM, it depends on your servers. So there's servers where you can have 6 slots of memory and you can configure them to be like a RAID 5, where you can literally swap a drive. Sorry, that's me thing. So this is server dependent. The operating system just assumes that memory is fine. Yeah? NVDIMMs like ECC memory have extra bits on them to ensure bit flips and so don't happen. But if you want to like literally like a hard drive in an array to swap one, some servers have capabilities of putting memory into like mirror mode or a RAID 5 mode for memory. That's all done on the main board. The OS has no idea about it. It reduces the amount of memory you have, but it is technically possible. And it might make sense when you start storing stuff there. Yeah? Technically, Intel says that neither of them like dies, but thing is, you still should do backups. Yeah. So that's that. So is SQL Server restart required after configuration? No, it's not. When you turn it on, it just starts using it from there on. Yeah. Thing is, and when you turn it off, it will take a while for all the data to go back to a regular. So that persistent memory, when you turn it on, when you turn it off, it still keeps the data file on the persistent memory. It just will transfer the data to the buffer pool all the time. While when you turn on hybrid buffer pool, it will only transfer it to the buffer pool if it has to modify it. If it just reads it, it keeps it in the persistent memory. Yeah. If you turn it off, it's a file like every other file. Okay, more questions. So the next question is the data will come inside the hybrid buffer pool. So to understand that one more time, I'm pulling up the slide again. Yeah, this is just the green area, the big green area below the PMEM chip is just another data file. It's the same data file as here. The difference is it's not stored on a regular drive. It's stored on that persistent memory drive. Yeah, that was formatted in direct access mode. Yeah, that's a difference. It's a file from the OS. It's just another drive letter where you put the file. So this is how it gets in there. You can use one big one for one database. You can put 1,000 small files for 1,000 small databases in there. Yeah, no difference. As long as they're all multiples of 2 megabytes, it's just fine. So there's no special command to move it there. You just create it on that drive letter. You can create folders. You can do everything you do in a normal file system. Yeah. So there's nothing special to move it in there. So please explain Tim's MDF and NDF as well with file group approach, please. So that's a lot to explain. First of all, the endings MDF and NDF are randomly chosen. One is for the main data file and the other one is for the secondary data files, as I like to remember it. It doesn't matter. You can call your data files whatever you want. It's just common use that you call the first MDF and the other one's NDF. What's actually inside them doesn't matter. Yeah, you can put just one file in the buffer pool. What normally makes sense is to put the whole file group there, because if you don't put the whole file group there, your data will be randomly in the hybrid buffer pool because you have no control where to put a file within a file group. You can choose where to put data on a specific file group through partitioning or through creating the table on that file group. But if you have multiple files in that file group, you have no control in which file the data goes. SQL Server uses an algorithm, and that algorithm can never change, and it will just keep using them in a kind of round robin fashion. That's as far as we have time for answering that. So if the log buffer is already in a DIM, how does it move to an NVDIM or better performance when they're both in DIMMs. So NVDIMMs can have the same performance as a regular DIMM, so there's no difference. This only happens when you start SQL Server. You can turn on the hybrid buffer pool while SQL Server is running. If you want to use an NVDIMM, that NVDIMM is in there. And when you start SQL Server is using it. There's no turning it on or turning it off. Yeah. So when SQL Server starts and the server has an NVDIMM, which is the one with the battery, it will just use it. Yeah. You have no control over that, and that makes it really, really useful. So I hope that answers that. Yeah, so the next question is, someone had 20 milliseconds IO on regular SAN and they moved it to an extreme IO, which is basically the same as in my legacy slide, the Dell, the pure array thing is, and it was 1 to 3 milliseconds max. Yeah, and that sounds absolutely what I would expect from it. Yeah, you have all the performance gain from the flash, so internally that system doesn't have any performance issues more, but it still has to use the network to communicate. So you will not go below the, you can go down to half a millisecond if you use really good controllers and drivers, but 1 to 3 milliseconds, yeah, that sounds totally normal for an extreme IO. If you would have put the same money and used NVMe drives into your server directly, you would be 10 times faster, but 100 times faster even. So yeah, but that's exactly what I would expect. Are NVMe SSDs reliable for storing T-log files? Yes, they are. You just have to buy the right kind. So the very early SSDs were really bad in wearing out because you can only write between, depending on how an SSD is made, between 2,000 and 100,000 times write to it. So if you write to your log file 5,000 times and you have a 2,000 write disk, it's going to be broken. Yeah, thing is, that was in the beginning. Today, these numbers changed massively because the drive manufacturers get clever. They're not writing the same data to the same location all the time. So what you have today is you have a value on every SSD, a specification that is called drive writes per day. This basically says, how many times can you write the whole capacity of your drive every day before it breaks for 5 years? So let's make it very simple. You have a drive that is 1 gigabyte in size, which is super small. Nobody has a drive more than that. That means every day you can write 1 gigabyte to that drive for 5 years, and the drive will not die if it has 1 drive writes per day. There are drives out there that have 25 drive writes per day. So that means you can write 25 gigabytes on that drive every day for 5 years, and it will not break. So let's go to a practical size. Practical size is probably a terabyte or larger, and your log file is a couple of gigabytes. And then you take a drive write of, let's say 25. So that means you can write 25 terabytes per day. That also means you have 25 terabytes of transaction log backups a day. If you have that, you can afford more than one drive every 5 years. Yeah, because then you have an insane amount of data. But just do the simple math. How much log writes do I have per day? This is how much log backups do I have per day? How big is my drive? And what's my drive writes per day? With that, you can easily calculate how many years your drive will last. Currently, most of my systems have NVMe drives in the 4 to 8 terabytes. I dedicate one of them for transaction log files. Thing is, yeah. Redundancy, in my perspective these days, is achieved through features like always on availability groups and not through expensive storage. If you're super paranoid, you can still put NVMe drives on a RAID controller and mirror them. Be careful that you use 2 different drives, because if you use the same drive, they will die on the same write. The next one, will performance of query store get affected using the persistent memory? I don't know. I guess if you put the database that holds the query store on persistent memory, it will change. Other than that, I don't know. I don't use query store, sorry. Can't help you there. In hybrid buffer pool, is it like actual data file or on buffer pool or rather than on disk? No, it's an actual data file when you look from it from the OS, But when you turn it on, SQL Server says that's a data file, but I treat it like memory because I don't have to worry to write to it because it's just memory. Yeah? So depending where you look from the OS, you will see a regular file. Insert SQL Server, when it's turned on, it knows it's memory. Can you use NVDIM or persistent memory in storage space direct? And will it make sense? Yes, it does. You can use both. So technically you can use it NVDIM as your cache storage and persistent memory as your fastest thing is. The only problem you might have is that you need to invent a new network card that can actually transport that speed. But I've seen people use PMEM as the first line cache. So they used NVMe drives for storage and then PMEM for the thing is. I've never seen someone use NVDIMs and PMEM. Interesting. The problem is even PMEM is so fast that any current network card that you can attach to the server in a reasonable quantity will be the bottleneck, so there's no point in doing it. But technically, yes, you can. And that's the last question. Thank you, everybody, very much. If you have any more questions, let's go to my last slide and keep that up for a couple of seconds. Sorry. Oops. Here, this is my email address. You can shoot me an email afterwards if you don't want to ask the question in public or you wake up tomorrow. Thank you so much for watching. Thank you for attending this and trying to learn and make SQL Server perform better in the world.
Thank you, Thomas, so much for taking our time.
Yep, thank you. You're welcome.
And Thomas, you will kindly have to click on done in the Q&A panel for all those questions because we can't do that. Yeah.
Okay, I will click a lot. I've answered them all. I just didn't click on done. I just saw it tells me done.
Thank you.
Oh, they're all answered. Good. I should stop sharing so you can put up the vendor slides again, I guess.
Yes. Thank you. Thank you, Thomas. Have a good day. Rest of it, whatever it is. Thank you.
Yeah, it's early in the morning, but that's not a problem. Thing is, if you have any other events ever and you liked what I did, happy to come again. Greetings to everybody. Stay safe.